Hi everyone. Today's video will cover Chapter 2, which is the organization and graphic presentation of data. The first aspect we're going to cover is the organization of data. And in doing so, we're going to go back to one of our former concepts from Chapter 1, which is starting off with descriptive statistics. So if you'll recall from our last discussion in Chapter 1 about the difference between descriptive and inferential statistics, descriptive statistics allow us to simply describe certain aspects of a data set, a sample, or if we have access to the entire population. Whereas inferential statistics allow us to make inferences or generalizations about the material. But today we're going to be primarily focusing on descriptive statistics. And the way that we can go about doing that is by displaying different forms both graphically and through actually calculating certain forms of statistics themselves. And so we'll learn how to formulate frequency distributions, how to calculate proportions, percentages, ratios, rates, and percentage change. And then the second half of this video, we'll go over how to display that in a manner that's very readable and accessible to our general audience. And in this case, we'll go over pie charts, bar graphs, histograms, maps, line graphs, and time series charts. The first organizational technique that we will be discussing is a frequency distribution. And a frequency distribution is a way for us to organize data to show how often each value or category occurs in a data set. It also helps us summarize and visualize the distribution of data, and it makes it easier for us to identify patterns such as central tendency, spread, or skewness, which we will also talk about later on in this semester and in future chapters. The two central components of a frequency distribution that you will see on the chart we'll talk about in just a moment here are values and frequencies. Values are the different outcomes observed in your data. So if we were looking at things like age groups or income levels or different response categories in a survey question, which we also saw in Chapter 1. The second is frequencies, or how many times or the number of times each value or category appears. And I think with our example here, this will make a little bit more sense in broader context. So let's take this example of a frequency distribution. And if you've ever used Microsoft Excel, this should look fairly familiar to you as it follows that spreadsheet format. This particular survey question asked students, do you support the death penalty? And the options that they had to choose from in this survey question was no, yes, or I don't know. So these are our values listed here in column 1. The numerical values that you see in the other cells here represent our frequencies, or how often did these people respond to a certain category. So if I was curious how many individuals did not support the death penalty in Class 1, I would first go to my Class 1 column up here and then look at how many people did not support the death penalty, and I'd find that it was 5. 5 students did not support the death penalty. I can also look at other aspects too. Maybe I'm interested in my third class, Class 3, how many people said they were unsure or they didn't know if they supported it or not. Again, all I have to do is go over to my column here under Class 3 and see how many people selected I don't know, and I see that 3 students said they were unsure or they didn't have a strong opinion about the death penalty either way. The last thing I want to note about a frequency distribution is our total row here at the bottom. And so what this does is explains to us the total, or how many individuals responded to a given survey. And in this case, in Class 1, we had 14 students respond. We had 13 students in Class 2, and in Class 3, we also had 14. A way for us to check our math on this as well is if I add 5 plus 7 plus 2, I get a grand total of 14. Similar to Class 2, if I add 8 plus 4 plus 1, I get a grand total of 13. And lastly, with Class 3, if I add 5 plus 6 plus 3, I get a grand total of 14. And so that's a way to ensure that our cell sizes, or these individual frequency values, end up calculating out to the sum total of how many students in this case actually responded to the survey. Another central component of frequency distributions oftentimes is a category called a proportion, which is often designated in a column by itself. In this case, a proportion represents a part, share, or number considered in comparative relation to a whole. So basically, that's a fancy way of saying how often did one of these outcomes happen relative to the entire group. And we'll discuss this in just a moment. But before we get back to our class example about support for the death penalty, I want to draw your attention here to this formula on the right-hand side of your screen, which represents our proportion calculation formula. You'll see underneath here with the bullet points that P represents what we're actually trying to calculate, which in this case is proportion. Frequency is represented by this F here in our numerator. And lastly, our capital N represents our total, or how many people filled out that survey or were a part of that in the first place. So let's look at this in context. Again, I borrowed over here our proportion formula from the last slide, so this is what we'll keep in mind as we're calculating each of these. So if I was interested in calculating the proportion or the share of individuals in class 3, which is what we're going to be taking a look at here for the next couple slides, and if I wanted to know this share that said, no, I do not support the death penalty, all I have to do to calculate that proportion is take my frequency value, or again, that raw value, and divide it by our total. So in this case, I'm getting my frequency value of 5, and plugging this into my proportion formula here and dividing that by the total. So in this case, I had 14 total students that responded to that survey, and you can double check yourself down here to ensure that you're having the correct value. If I do 5 divided by 14, I get 0.36. So that is my proportion of students that did not support the death penalty. If I wanted to calculate the proportion for students that did support the death penalty or responded yes, I just follow the same formula and steps I did when we calculated for no. I take my frequency value of 6, plug that into my numerator here in our formula, and divide by our total of 14 to get a grand proportion of 0.43. And lastly, I can do that for my I don't knows as well, or students that didn't necessarily have a strong opinion either way in terms of support for the death penalty. All that I take is my frequency value here, plug it into my numerator, and divide by the total. Something that you may have noticed from our last slide is that proportion values have to be a value between 0 and 1. If you ever calculate a proportion value that is less than 0 or greater than 1, make sure and go back and check your work because something probably went wrong there. The reason being is that proportion total values should always equal 1. So if I add together, similar to when I did on the last slide, 5 plus 6 plus 3 equals 14, if I add together 0.36 with 0.43 and 0.21, I get a total of 1, which represents the entire share of the class. So if each individual cell, for whatever reason, did exceed the value of 1, again, check yourself for a calculation error there. And again, this is just another way for us to organize our data and demonstrate to our reader in a different way how we want to represent our data. So the first aspect of that frequency distribution is our frequency column here, which again represents our raw numbers, just simply how many people responded to each category. And our second way is to say our proportion, or what share of the class responded in a certain way. Another way that we can display and organize information in a frequency distribution is through the use of percentages. And so percentages are a proportion or ratio that is expressed as a fraction of 100. And you've probably seen this symbol quite frequently before, which is our percentage symbol here. So we'll be using that here as well. And all you have to do in order to convert a proportion to a percentage is simply multiply that proportion value that we just did on the last slide by 100. And so if you take a look on the right-hand side here for our percentage formula, you'll see that this aspect here of the P equals F which is our frequency, divided by n, is our proportion formula. All that we're adding here to calculate our percentage is this multiplication factor by 100. And so let's take a look at what this would look like in terms of our example with support for the death penalty. So again, same idea here, borrowing my percentage formula here from the last slide. All that I'm doing here is taking our frequencies, dividing them by our total. So in this case, if I wanted to know the percentage of students that did not support the death penalty, I just take 5 divided by 14, multiplied by 100 to convert that into a percentage. In this case, you can see that all I did as well is move this decimal point 2 spaces, which again indicates that it was multiplied by a value of 100. The only addition here is this percentage symbol. And this, again, is just a way for us to communicate to our reader what share or what percentage of the class responded in a particular manner. In this case, I could say that 36% of Class 3 said they were not in support of the death penalty, whereas 43% were in support of the death penalty, and 21% didn't have a strong opinion either way. They didn't know. Moving on from frequency distributions, which again only show us one variable, and what we saw in our examples there is support for the death penalty or not, even though it had a couple value options with yes, no, and I don't know, the only question that we asked again was support for the death penalty. Did you, didn't you, or didn't you know? In this case, a frequency distribution that measures 2 variables is called a bivariate table. So in this case, bi means 2. You should recall that from our chapter 1 discussion about the difference between univariate, bivariate, and multivariate analyses. So in this case, bivariate tables, which are also referred to as crosstabs, if you see that in the book or in Excel language, is a statistical tool that is used to examine the relationship between 2 categorical variables. We can use this information to calculate both percentages and proportions, so those formulas we just used on the latter slides. Variable 1 we often display in a row, and variable 2 is often displayed in a column. So again, if you're familiar with Excel, this should look pretty familiar to you. Let's take a moment here and pause the video and ask yourself this question. Given this information here about variable 1 and variable 2, with this example above, please identify what is variable 1 and 2 in this example. Okay, if you pause the video, you should know that variable 1 are those that are displayed in the rows. So in this case, it's class rank. So I have freshmen, sophomores, juniors, and seniors. And my variable 2 is going to be displayed in a column. And that question here is, do you live on campus? What I can see here as well is that there were 2 options, whether they lived off campus or on campus. And so those are our 2 variables. Again, in my rows here, let me put a little R to designate that here in our columns at the top, we can now compare the relationship between these 2 variables in a pretty easy manner. What we might suspect is that freshmen oftentimes are required to live on campus, and so we can see that, yes, one of our frequency totals is much greater for freshmen to live on campus in comparison to freshmen who don't live on campus. And if I wanted to know the proportion of freshmen that lived on campus, all I would have to do is do 100 divided by 137. If I wanted to know the proportion of students that did not live on campus, I would take 37 and divide that by 137. Ask yourself this question. If you calculated those to be the proportion values, what is the next step you would have to do in order to calculate a percentage? Remember, our proportion and percentage formulas are very similar. The only thing that we need to do to convert a proportion into a percentage is multiplied by 100. So keep that in mind as you're looking at bivariate tables or crosstabs. So let's work through an example of this. So let's use our knowledge of crosstabs or bivariate tables to answer the following research question. Let's say a researcher was interested in answering the question of whether or not there was a relationship between people's belief in aliens and where they grew up. Perhaps this researcher thought that folks from rural areas might be more inclined to believe in aliens because they've seen things such as crop circles before, whereas folks from urban jurisdictions may not have had experience with these, and therefore they may not actually believe in aliens at the same frequency as their rural counterparts. But that's where statistics and research can come into play. We can actually test this out. And we can use the following frequency distribution to answer this research question, which is, what is the percentage of people from rural areas that believe in aliens? So, importantly in this case, I'm not necessarily concerned with the entire total of our frequency distribution, which indicates to us that 26 individuals were asked this question, but I'm only concerned with the individuals from rural areas. So in this case, I'm only concerned with this column, this very first one. So it's 11 total individuals said, I am from a rural area. And all we have to do is take a look at the frequency or the number of individuals that said, yes, I do believe in aliens. And in this case, it is 6. So all we need to do in order to calculate the percentage is take the individuals that said, yes, I do believe in aliens, which in this case was 6, and divide that by the total number of people that indicated they were from a rural area. So that's where I'm getting this 11 figure down here. If I were to have asked you just to calculate the proportion, all you would have had to do is stop at this step here. It would have just been 6 divided by 11. But in this case, the research question is asking specifically for a percentage, so we need to multiply our proportion by a figure of 100 to get to a total percentage of 54.55%. So in other words, a way that we could interpret this problem within the context of the research question is to say that 54.55% of individuals who grew up in rural areas believe in aliens. We can also use this to answer other types of questions. Let's say we were interested in calculating the percentage of people who believe in aliens that are from a rural area. So this is asking a slightly different question. In this case, of the people who believe in aliens. So we want to go to our yes category here because we're only interested in folks that said, yes, I do believe in aliens. Of those people, how many of them grew up in a rural area? In this case, I'm going to take my frequency total here, value of 6, and divide that by my row total here of 12. So of the people who said yes, which in this case is 6 plus 4 plus 2 equals 12, how many of them said yes? So again, all I'm taking in my numerator value here is 6, dividing that by our total column of 12, and multiplying that by 100 to get a percentage total of 50%. In other words, the percentage of people who believe in aliens that are from a rural area is 50%. Another way that we can utilize frequency distributions is through organizing interval ratio level data. If you recall from Chapter 1, interval ratio level variables are those that do have a numerical value attached to them, and there is a measurable distance in between them as well. So oftentimes we're talking about scores that have numbers attached to them. So let's say I ask a group of students, how many hours do you spend per week studying? In this case, what we're looking at here on the right-hand side is simply the raw totals, or what were those numbers that they reported to me. The way that I have it formatted right now is not the best in terms of my ability to communicate this information to a broader audience or to identify any patterns or trends that might give us an indication of how often our students are studying. A way that we can utilize frequency distributions to help us organize this data is through the use of intervals. And so I can do step by step through our raw data here using intervals to get to a result that looks like this table over here. To use and create an interval table, there are 3 aspects that we must make sure that we abide by in order to create the table, and those are listed here. So let's go through each one individually. The first is that our intervals must include the entire data range. And what I mean by that is that we must include the lowest value and the greatest value and make sure we're not leaving any out in between. So in this case, I see that my smallest value is a student that reported that they spend approximately 3 hours studying per week. And my greatest value is right above them here, a student who responded that they spend approximately 32 hours per week studying. So there we have to make sure that our intervals include a range from 3 to 32. So we'll have to keep that in mind. That's step one. Our intervals must also be equal in size, meaning that each of these row categories have to be identical in their structure. In this case, I chose an interval value of 10. So each of these intervals here have 10. So 0 to 9 hours is 10 total, 10 to 19 is 10 hours total, and 20 to 29 as well. And then 30 or more kind of collapses our last category here, but we know that we still included our highest value here of 32. So again, identical in size, in this case, our 10 value. Lastly, they must be mutually exclusive. What this means is that these intervals cannot overlap with one another. So for example, I could not create my first interval to be those that studied between 0 and 9 hours, and then have my second interval be those that studied between 5 and 15 hours. Reason being is that that would result us in double counting certain observations. In this case, there would be people who fell into both of these categories. We had some people who indicated that they spent about 8 hours studying per week. So if I did not make my categories mutually exclusive, meaning that they overlapped, I would have someone here both in the 0 to 9 category because they said they studied 8, and someone in this category because they also said 8, but I had my interval listed as 5 to 15. So you can see where we run into a pretty sticky area there. So that's something to keep in mind as well. So again, to calculate these areas using intervals, these are the 3 aspects that we must make sure that we abide by as we're creating that table. And what this allows us to do overall is convert our raw data here, which is what we started with on this side, and create a much more legible chart over here. And so what this shows me is that a good chunk of students are only spending about 0 to 9 hours studying per week. Whereas as we get to higher values down here of 10 to 19, 20 to 29, and 30 or more, we kind of dwindle off. And so what I would conclude from looking at this chart is that most students are spending between 0 and 9 hours per week studying. So I want to return to our original discussion about frequency distributions, but still keeping in mind that we're using interval ratio level data here. What I did was transfer our information from the chart we just created using intervals onto this new frequency distribution here. So what we can see is that those intervals from the very last slide have been transferred over here. And I want to give you the opportunity to practice calculating both the proportion and the percentage columns on your own. Keep in mind that when you're going through this, your proportion total should equal 1, and your percentage total should equal 100%. When you're going to go and calculate these, if you round them to the 100th spot, there may be a little bit of a rounding error in the end. So if you end up with a total around 0.99 or 1.01, that's totally okay. Same goes for our percentage column as well. So go ahead and work through this individually, and on the next slide, I will show you the outcomes of this frequency distribution, and you can compare it to your own calculations. Okay, so this is your opportunity to compare your own calculations to what I have listed here in my answer key. In this case, to calculate the proportion of students who said that they studied between 0 and 9 hours per week, all that I did was take our value of 5 and divide that by 12 to get a value of 0.42. Same goes for the next steps here in the rest of the column. Remember that the relationship between proportions and percentages is simply moving the decimal point 2 spaces. So if I do that, I get 42%. Or the other way to go about that is simply multiply your proportion value by 100. Each of these values should get us to approximately 1 as our total here, as well as our 100% column total here for overall percentage. One last note I wanted to touch on in terms of frequency distribution were these last two columns here, which you may see pop up in your text or in other review problems, and that is cumulative frequency and cumulative percentage. So I'll just briefly talk through both of these. Cumulative percentage is calculated by adding together all the frequencies from row to row. So in this case, I got 5 because I didn't have any other row to mention except for my 0 to 9 in this row. To get this 8 total, all that I did was add the next row total to it. So I took the value of 5, added it by 3 to get 8. Now I take my total from the second row, and it's accumulating over time. That's where that term comes from. In this case, my next row had 2, so I do 8 plus 2 to get 10. And lastly, I had 2 students who said they study 30 hours or more, a week. And so that gives us a cumulative total of 12. And so your cumulative frequency should always mirror your column total from your frequency here. So that's a good way to check yourself. Lastly, cumulative percentage is the exact same idea as cumulative frequency, except we're adding together our cumulative percentages as we go along. So 42% plus 25% gives us a grand total of 67%. If I take 67% and add it to 16.7%, I get a total of 83.7%. And lastly, if I add 83.7 to 16.7, I get a grand cumulative percentage total of 100%, which again should mirror our total percentage here. It's just another way for us to be able to understand how our intervals may interact with one another and see those trends over time. Statistics such as frequencies, proportions, and percentages can be really helpful for us in terms of organizing and communicating data. Another one that we're going to jump to now is calculating rates. And so rates are a measure that quantify the frequency of an event or characteristic relative to a particular unit in time, population, or other type of denominator. This is calculated using the number of actual occurrences divided by the number of possible occurrences per some point in time. So oftentimes you'll see rates expressed in terms of multiplied values by 10, 100, 1,000, 10,000, etc., etc. As criminologists, we frequently use rates to communicate information about large samples and populations. In this case, what we're looking at here is the states with the highest opioid overdose death rates for the year 2016. And in this case, I'm going to use the example of the state of Kentucky here at the bottom. And so if I was curious to know the rate of drug overdose deaths in the state of Kentucky, all that I have to do is take the number of overdose deaths and divide that by the number of people in the state. And so that's where I get my number of 1,419 from this chart. And then the last time I looked up the population of the state of Kentucky, it was approximately 4,235,800 residents. Oftentimes in social sciences, we will express rates as per 100,000. And so that's why I'm using that multiplication figure here. You can also express rates in values such as 10,000 or even a million, but this is the one that you'll see most frequently both in your book and other forms of media and text. When I take the value of 1419, so again 1,419 overdose deaths, and divide that by the population, I get a value of 33.5 overdose deaths per 100,000 people within the state of Kentucky. And that's important to note. It's not per the United States. If it were, we would have to add all of these totals together and gather them from the other 40 states and divide that by the entire population of the United States. But let's say there was a Kentucky legislature that was interested in only knowing how it affected their own state. They could use the statistics of rates to be able to communicate how frequently or how often this is occurring to the residents of their state. Another statistical technique that we can utilize is ratios. In this case, a ratio is a quantitative relationship between two numbers, and it shows how many times one value contains or is contained within one another. It's very easy to calculate ratios because all that we have to do is identify the first frequency that we are interested in and divide that by the second frequency. In this case, a frequency is any of the number of cases within a respective category, and so essentially all that we're doing is to calculate a ratio is dividing the frequency by one category by the frequency of the second category. So let's see how we actually calculate this out. So let's revisit our example regarding support for the death penalty. In order to calculate a ratio, all that we have to do is identify our frequency 1 in comparison to our frequency 2. So let's say I was interested in determining the ratio of people who support the death penalty in comparison to those that do not. So my frequency 1 is who we're going to identify first. In this case, it was the people who support the death penalty. So we're going to get that answer from our research question itself. And so that's my frequency 1. I take the folks that said, yes, I do support the death penalty, and that's where I get our numerator here of 6. Second, I only have to identify our second frequency here, which is in comparison that those that do not support the death penalty, where all I have to take are my no values here and plug that into my denominator for a value of 5. So if I take 6 divided by 5, I get a total of 1.2. So let's interpret this within the context of the problem. The ratio of supporters of the death penalty to non-supporters of the death penalty is 1.2. This means that for every one non-supporter, there are 1.2 supporters. We can also extrapolate this up by simply multiplying these values to figures that make a little bit more sense to us. It doesn't necessarily make sense to have 1.2 persons, right? So another way that we could interpret this is for every 10 non-supporters of the death penalty, there are 12 supporters or 12 people that are in favor of its use. As a brief summary of these sections, I want to just spend a moment discussing the differences between proportions, percentages, ratios, and rates. So as a reminder, percentages, proportions, and rates are utilized to summarize the overall distribution. Recall that we did our examples via a frequency distribution itself. However, ratios express the relative size of the categories themselves. So what we just calculated with our death penalty example is what is one size group compared to another. And so here we're using more just of descriptive statistics and simply summarizing our overall distribution, where here we're looking to express the relative size of each respective category. Again, in our example of the death penalty, it was the relationship between supporters and non-supporters. Another statistical technique that we can utilize is percentage change. And percentage change is a concept that quantifies the degree of change over time, but it is expressed as a percentage. So it tells us how much a variable has increased or decreased over time. What I have listed here is our percentage change formula. Our denominations here of both F1 and F2 are listed, in which frequency 1 is expressed as our first score and frequency 2 is expressed as our second score. So we're still using a lot of the same ideas that we've used from our frequency distributions, calculating proportions and percentages, and even ratios, but just doing it in a format where we can now trace something over time instead. Percentage change is actually fairly easy for us to calculate. All that we have to identify is our first frequency, designated by F1, and our second frequency, designated by F2. In terms of percentage change, F1 is going to represent our first time period. Our frequency 2 is going to represent our second period of time. So let's say that I was interested in understanding the percentage change in the name Anna between the years 1920 to 1930. Our first time period, or F1 in this case, is the year 1920, And our F2, or our second frequency, is going to be from our second time period, which is 1930. So the information that we need in order to identify both F1 and F2 is located in the chart here on the left. So I'm going to go to our x-axis here and go to the year 1920 to see that approximately 19,000 individuals were named Anna in the United States in that year. So that is where I'm getting this value here for our F1. So you'll see it both expressed in our numerator and denominator. Secondly, I have to go to our second time period, which in this case is the year 1930, to see that approximately 10,000 individuals were named Anna in the United States in that year. So once I plug those in, I simply put in my F2, subtract it by my F1, and divide by F1, and then multiply that total figure by 100 so that it can be expressed as an overall percentage. And so once I plug in all my numbers here, I receive a total value of 47.368%. But we know that this is actually declined. And so it's important to note here that we actually have a negative value. So it has decreased over time, or a value of negative 47.368%. In other words, to express this and understand it within the context of this problem, the number of Annas born between 1920 and 1930 fell approximately 47.368%. This word here, fell, indicates to our reader that it actually decreased. We can also think about this in terms of criminological examples. So let's say that I, as a researcher, was interested in understanding the differential rates of conviction for crack cocaine between the years 1980 and 1990. My first step would be to figure out what my F1 is, or my first frequency, in the year 1980. So I would have to determine how many individuals were convicted on possession of crack cocaine within that given year. My frequency 2 would be that second time period of the year 1990. And I would also have to determine how many individuals were convicted of possession of crack cocaine at that time. All I would have to do then is plug that into my formula here and multiply that by 100, and we would be able to tell as criminologists whether the rate of conviction has increased over that 10-year period or whether it has decreased. And so you can see some of the applicability that percentage change can have within general conversations, such as this with our example of Anna, but also criminological and broader societal issues as well. The first half of this presentation was dedicated to the idea of organizing our data in a way that makes it the most readable to a broader audience, whether that's through creating things such as frequency distributions, calculating proportions, percentages, rates, and ratios. But now I want to spend a little bit of time revisiting a topic from Chapter 1, which is the graphic presentation of data. The first type of graphic that we're going to talk about in a little bit more detail is a pie chart. And a pie chart is a circular statistical graphic that is divided into slices to illustrate numerical proportions. So recall from earlier in this presentation that a proportion is a share, or just a portion of an overall sample or population. To see this illustrated, let's take a look at the right-hand side graphic here in terms of how many people are incarcerated in the United States. The circle as a whole, or the entire pie, is showing us how many people are incarcerated throughout the United States as a whole. However, each of these slices is dedicated to demonstrating to us what proportion or what share of those incarcerated folks are within each different type of facility. So whether that is local jails, which looks to us to be a little bit over a fourth of our incarcerated population in the United States, where state prisons, which we see is more than 1.2 million incarcerated folks throughout the United States, makes up more than half of our incarcerated population. So this is a quick way for us to both display proportions we may have already calculated, but to do so in a way that shows a holistic image. So again, in this case, the entire incarcerated population, but also demonstrating additional information within that, or what proportions are in local facilities versus state penitentiaries versus federal jails and prisons as well. The second type of graph I'd like to talk about in a little bit more detail is a bar graph or a bar chart. Now, we briefly touched on this in the context of Chapter 1, but just to reiterate, a bar graph is a graphical representation of data that uses rectangular bars to compare different groups or categories, and the length of those bars is proportional to the value that it represents. So in this case, if we take a look at our chart here on the right-hand side, my y-axis is showing me the number of respondents. So it is proportional to how many people responded affirmatively to a question. In this case, do you prefer cats or dogs? I had 5 individuals who said I prefer cats and 6 individuals who said I prefer dogs. Importantly, though, within our broader conversation about levels of measurement, recall from Chapter 1 that we have nominal, ordinal, and interval ratio level data. In this case, a bar chart is going to be best for those that are nominal or ordinal variables. And so again, remember that nominal variables are those that do not have an inherent order. So what we're looking at here on the right-hand side, if I switched this cats or dogs category, this doesn't make any difference for our interpretation of the graph. Whereas ordinal variables are ranked in nature, meaning that there is some inherent order that makes sense for us to present it on our x-axis. Something that we had revisited from Chapter 1 was the idea of the mother's highest level of education. And so it makes sense for us to have on the far left-hand side of our x-axis that the lowest amount of education would be on that left-hand side, and it would be ordered in a way in which each subsequent level of education was higher than the next. And so keep that in mind as you are both creating bar charts and viewing them as a reader. Another type of graphical representation is a histogram. Now, visually, this may look pretty similar to a bar graph or a bar chart, but there are a couple nuances in between that I want to touch on because they do serve different functions. So a histogram is a graphical representation that is used to visualize a distribution of a data set. And one of the key differences here is that it displays the frequency of data points within specified intervals, which are also called bins. So if you see this term pop up either in future presentations or in your book, this is a good reference slide to look back on. Histograms are commonly used in statistics to show how this shape, spread, and the central tendency of continuous data operates within a variable. Histograms are very similar to bar charts. However, one of the key distinctions here is that histograms use interval ratio level variables. Recall from the last slide that bar graphs exclusively use either ordinal or nominal level variables, and so that's one of the key differences here. The intervals are also used to determine the bars. And so what do I mean by intervals? What is this idea that I've alluded to up here, as well as this idea of bins? So when using interval ratio level data, recall that those are ones that have a numerical attachment to it. It's something that can be quantified. It has a number attachment to it. So an example of an interval ratio level variable is what we have right here, which is GPA. In this case, I surveyed a group of students to see what their current grade point average was. In terms of this idea of interval or bins, you can see down here that I currently have our interval set at 0.1. So what does that mean? On my x-axis here at the bottom, each of these bars is 0.1 away from each other. And so what this shows us as the reader is that each of these bars is representative of a 0.1 of a grade point average. In other words, starting here, we have one individual who received a 2.1 GPA. And I know that because I'm looking at my frequency here, and this would be the ticker for the 1. And each of these subsequent steps would be 0.1. So that's what I mean by my interval or my bin size, until I hit my next ticker point, which is 2.5. In terms of histograms overall, in terms of showing us either continuous data in the shape and the spread, One thing that I can visually recognize right away within this particular graph is that most people have higher than a 2.0 GPA, right? We have clustering here on the right side of our graph, which indicates to me that a majority of my students that I surveyed have higher than a 3.0 GPA. But let's take a look at an example if I were to change this interval size here at the bottom. This is representing a histogram with fewer bars, but it is the same information that I just used on my previous slide. The difference here being is that I increased my interval rate to be 0.25. So now the difference between here at the bottom is only 0.25 rather than just 0.1. And so let's take a look at what actually happened here. I had two students before on the previous graph who indicated that they had a 2.1 GPA and a 2.2 GPA, so one of each. Now that I've increased my interval size, you'll see here at the bottom that they have been collapsed into one bar. So I have two students that are in between the 2 to 2.5 range. So as my interval size increases, I'm going to have fewer bars on my histogram. And you can go back to the previous slide to see what that difference is. Let's see what happens if I increase my interval size to 0.5. Again, I see even fewer bars because now I'm collapsing more of my observations into just one category here. So again, I have even fewer bars. And this is a decision we can make as both social scientists and criminologists of how we want to display this data to our reader. Perhaps it's important for us to show each individual nuance of that 2.1 to 2.2 and 2.3. Maybe we want really granular analysis. In that case, it might make sense for us to go with that first iteration of the graph where those interval and bin sizes at the bottom were only 0.1. But perhaps we just want a more general idea of where our students are. Perhaps it makes more sense to just keep our intervals at 0.5 so that we get a quick visualization that, hey, our students are pretty smart, right? Our frequency levels here are in the mid-20s for those that are between a 3.5 and a 4.0 GPA. But something we have to be mindful of and careful of is having too few bin sizes. So let's take a look at what that might look like in the context of this example. Let's say that I created only one bin size or one interval. In this case, that means that all of my observations, meaning all of the students that I surveyed, got collapsed into one category here. And you'll see that my y-axis changed as well to accommodate this, because now I have upwards of 50 individuals that all have to be into one bar. Because of that, I can't see any of the variation in terms of overall GPA. And so that's an issue here. When we have too few bins or too few intervals, we lose a lot of the nuance of our information. And so when we are making those decisions as social scientists about how we want to display our graphical information, this is a key point that we can look to determine how we want to do that. How do we want our x-axis to be formatted? And we can do it in a bunch of different ways. All four iterations of those graphs are technically communicating the same information, right? But we can visually communicate that in a different way. Another form of graphical representation that we touched on briefly in Chapter 1 is a line graph. So line graphs are a type of graph that are used to display information as a series of data points that are called markers, and they are connected by a straight line. Oftentimes, we will use line graphs to show changes over time, but we can also use these for any type of interval ratio level variable. So again, that's a key distinction from other types of graphs that we've gone over so far. We can also use this with multiple lines and multiple axes, and oftentimes these are displayed in our next type of chart, which is a time series chart, which is a form of graphical representation of data points that are displayed in chronological order. Again, we are measuring changes over time. So oftentimes with time series chart, our x-axis here at the bottom is going to be some form of time, whether that's year, month, day, anything in that nature. We also saw back in our example about the use of the name Anna that it can also be measured in decades. And so time series charts are primarily used to visualize how that particular variable changes over that time period that's listed on the bottom of our x-axis. And this type of chart is very useful for identifying trends, patterns, and seasonal variations. In this case, let's take a look at our time series chart that's here on the right-hand side of the slide. What we're looking at here is the incarceration rate of inmates incarcerated under state and federal jurisdiction from the years 1925 to 2014. And because we're tracking this over time, what we can see is that there is a sharp increase that happens starting in about the year 1980. And so what we can look at is what type of policies or what were we enacting in that period of time that would cause such an increase in our incarcerated population. If you've looked at this in other courses, you may know that the tough on crime era policies such as mandatory minimum sentences, truth in sentencing laws, things of that nature really contributed to the increase of our incarcerated population throughout the United States. But by graphically showing this, we can communicate information about our incarcerated population relative to those policies. So knowing that those policies took place during this time, we can kind of show a cause and effect relationship between our two variables, which is, did this policy cause our incarcerated population to increase during this time? And with these visuals, yes, we can see that it increased starkly over that time period. Wrapping up our conversation with just a few more graphical representations is a scatter plot, which is a type of plot or mathematical diagram that uses coordinates to display values for typically two variables. So, as we've done with all of our graphical representations and charts up to this point, let's first take a look at our title. What are we viewing here? In this case, the research question is, how safe do you feel walking alone at night? Second indicators for our two variables in this case is to look at our y and x axes. In this case, our y-axis is measuring violent crimes per 100,000 residents, and our x-axis is looking at the percent of people who feel safe at night. In this case, we would suspect that individuals who live in higher crime areas may feel less safe, and that's what the researchers did find in this case. This downward negative trend line shows that as you are in a less crime-ridden area, which is this bottom half of the y-axis here, the more you feel safe at night, which makes sense to us overall. But each of these individual data points represents a singular person. So that's something that distinguishes a scatter plot from a line graph. What we can do, though, is institute what's called a trend line, which is this negative slope here, to show the overall trend of responses. One other type of chart that you may have seen within the criminological space is a flow chart. And so what you're looking at here is the overall entry and exit system of the criminal justice system. So after a crime is committed, this is showing all of the subsequent steps that you may have to go through as a defendant in a criminal trial. So whether or not you are moving into a juvenile defendant stage, or if it's a felony stage up here, what a flow chart does is show you all the different options and what your various outcomes could be, which are on the latter end here. The last one that we'll cover is a pictograph, which is a visual representation of data that uses icons, images, or symbols to represent quantities or an overall number. And oftentimes pictographs are used to depict instances that you want to show a stark contrast between data points. And so what we're looking at here in our figure 2 is the US incarceration rate by both race and sex. In this case, what we're looking at visually are the odds or the percentage outcomes in which each respective racial and sex category has in terms of their chances of being incarcerated throughout their lifetime. So what we can see here is that Black men who are ages 20 to 34 have a 1 in 9 chance of being incarcerated at some point. Where if we go here, which is white women ages 35 to 39, it's starkly different from these two groups, right? And what this pictograph is doing is visualizing this in a way in which each data point is a person. And so we are able to see this visually in a way that says, hey, this is a lot more common for Black men in this age group, right? 1 out of 9 chance. Whereas white women in the 35 to 39 age group have a much less chance, right? It's only this one figure here coded in black compared to the overall group. Okay, we have made it to the end of our chapter 2 video. And so, as I will do with all of our videos, is end with a summary slide. Again, this is a good test for you to see whether or not you understood the material that was in this particular video. And so in this case, a couple of questions you can ask yourself to kind of do a little bit of a content check on yourself is, what is a frequency distribution? Why do we use it, and how do we visually display that? Do you know how to calculate a proportion and a percentage? That would be important to note, both as we move forward with our different homework sets, but also quizzes. We also discussed bivariate tables, which are also known as crosstabs. So a little bit different in terms of frequency distributions, which use one variable. Remember that our bivariate tables use up to 2 variables here. We also learned how to calculate rates, ratios, and percentage change. And lastly, we concluded with just briefly talking about some different forms of graphical presentation, such as pie charts, bar charts, histograms, line graphs, time series, and scatter plots. So again, now is a great time to do a little bit of a content check on yourself, see what you might be missing in terms of content, and as always, if you have any questions, please feel free to reach out.